Hello, this is Team 24. This video provides an overview of the assigned soccer robot design assessment. The design project was to construct an entirely self-contained autonomous soccer robot capable of competing in the RoboCup Small Size League by scoring goals against multiple static robots or obstacles within a budget of $160. In order to achieve this goal, my team focused on developing a two-wheel differential drive design with one mounted camera capable of sending images to a Raspberry Pi single-board computer for processing, interpreting, and reacting to the soccer area environment. The design had to fit within a 180 diameter cylinder with maximum height 225mm without any dangerous construction. Furthermore, the body had to also house the mounting sensors and hardware without dropping them or tipping the robot while in operation. We did this by constructing a 3-level design using laser-cut acrylic with all major complicated structural fixings out of 3D printed black ABS. Furthermore, all gearing mechanisms and the cover were cut out of black acrylic, utilizing a living hinge technique. My name is Quinlan, and I was responsible for designing the robot's drive and electronic systems. Our robot runs off a differential drive system which consists of two 12-volt 100:1 gear ratio micrometal gear motors using laser-cut acrylic wheels with 2mm teeth. These DC motors and the dribbler motor were then controlled via two pre-made motor drivers which were capable of sending up to 3 amps of current forwards or backwards via PWM systems. These drivers were perfect for our drive system, capable of moving the robot forwards between 0.5 meters per second and 0.15 meters per second, well within the specifications. These motor drivers were then connected to the Raspberry Pi for GPIO input and control, and a custom PCB designed to regulate the 7.5 lithium-ion battery's voltage to the required 12 volts needed to power them. This voltage regulation was achieved by implementing two 12-volt low voltage regulators. This custom PCB was also responsible for providing up to 12.5 amps of regulated 5-volt voltage to the Raspberry Pi and solenoid. All electronics were housed within the second level of the robot to ensure close proximity to each other for better integration, and all exposed wires were covered in insulation for protection.
My name is Gao Yi, and I was responsible for the dribbling and kicking system. Our dribbler is made with a cylinder shape using rubber band glued to the surface to provide enough grip to handle the ball. After experimenting, the perfect height for the bar was 41mm high. The 30:1 ratio motor is fixed on the top of the bar and with a gear ratio of 1:1. This motor was chosen as it provided enough torque to be able to turn the ball well in contact with the field floor. The dribbler is effective at handling the ball when it turns left and right, forward and backward. Kicker is using solenoid system, which can provide 35 Newton force. The maximum kicking speed of the ball is 0.75 meters per second. This speed is achieved by connecting it with a voltage booster up to 30 volt. The solenoid is controlled using a transistor circuit within the custom PCB design.
Hi, I'm Dan Howard, and I worked on the vision subsystem of our robot. The objective of vision is to provide the data that AI navigation subsystem needs to function. So this data is a bearing and range for the ball, each goal, and up to 3 obstacles. It also provides a flag defining if the ball is in the dribbler and if the robot is too close to a wall. To get this data, we take images from the Raspberry Pi V2 camera and convert them into grayscale for walls and obstacles and the HSV color space for the other colored objects. For each object, we take the largest contour that is greater than a minimum area from pixels that are in a certain range. Calculations using the image and camera specs are then applied to return this positional data. This all needs to happen very quickly to give accurate data when the robot is moving, so the I/O operation of the camera is multi-threaded and a low-resolution image is used, resulting in around 20 frames per second.
Hi, I'm Dev Patel, and I'm going to run you through the navigation and AI subsystem. Our robot uses local reactive navigation approach to perform tasks like obstacle and goal detection. The data taken from vision subsystem is used for navigation purposes. We use two-stage reactive state machine approach for AI decision-making algorithm. Obstacles are treated as repulsive or attractive field depending on prior ball detection. Experimental data was collected for multiple scenarios the robot had to face. This approach requires less attributes for decision-making and increases processing speed.
With all these systems combined, our robot was capable of consistently scoring 2 goals per minute with up to 2 obstacles present in a wide variety of scenarios.